All right, welcome back in, everybody. In this video, we are going to look at a few repeated measures designs. And recall that repeated measures studies are also known as within subjects designs. So when you hear those different names, they mean the same thing. And this first question, it says the following data are from a repeated measures study examining the effect of a treatment by measuring a group of 5 participants before and after they receive the treatment. Is there a significant treatment effect using alpha of 0.05, two tails? All right, so the first thing to consider here is we're basically seeing, is there a statistically significant average difference or mean difference between these two measurements before and after these people, these 5 participants, received some treatment. And so we have the raw scores right here. And what you need to do is calculate some preliminary information. And so going over here to the formulas, you see this formula right here for D. D stands for difference score. And that's calculated by the second score subtracting the first score for each individual participant. And then once you get all those difference scores, you can calculate the mean difference or the average difference among all the participants. So I've actually gone ahead and calculated that information for us. And that's what's right here in this fourth column labeled D. D is the difference between these two scores. So for example, 7 minus 3 is 4. The average of these values, the average of the difference scores, was 4. And so that means that on average, scores went up by 4 points. And what we're essentially asking here is that a statistically significant difference? Did scores rise on average in a statistically meaningful manner, or is that just sampling error? Okay, so what we also need is the standard deviation of your difference scores. And so what I've gone ahead and done is I took my deviation scores where I subtract the mean from each score and then square that, add them all together. You get sum of squares equals 18. And then using your chapter 4 formula for standard deviation of a sample, the standard deviation S is SS, or excuse me, it's the square root. Let me write it actually just in case for your reference, is the square root of SS over n minus 1. Anyway, so that's what I used to calculate 2.12. And as you're going to see in a minute, we're going to need that information. All right, so let's go ahead and start with some hypotheses. And I'm going to write them up here. The first idea is that we're using a two-tailed test. And so with a two-tailed test, we're simply checking to see if the average difference is some number different than 0. In other words, if the mean difference score was 0, that means that on average, scores did not change. So that's what the null hypothesis is stating, that if everyone were given this treatment, the average difference in the entire population would be 0. And the alternative, on the other hand, is saying no, that this treatment causes some change, that the average difference score for the population is not equal to 0. And so we want to determine which of those two is the case. And to do so, we need to calculate our test statistic. In this case, it's a t-value since we're doing a t-test. And we're going to compare that to the critical value of t from the t-distribution table. And let's actually go ahead and find that. So before we go to our t-distribution table, we need our degrees of freedom for this study. And since there are 5 participants in the study, degrees of freedom is equal to 5 minus 1, which is 4. And we're using an alpha of 0.05, two tails. So now I'm going to go to my table. I'm going to find where it says 4 degrees of freedom, and then scroll over to the column where right here it says 0.05 in two tails combined. So it looks like the critical values are 2.776 on the positive side and negative 2.776 on the negative side. And so I'm going to write that right here. My t, I'll put critical. My t critical value is plus and minus 2.776. So as always, if our test statistic exceeds one of these values, if it's greater than 2.776 or less than negative 2.776, we will reject H0. And so let's find out what we have. The first thing we need is to calculate, in order to calculate t, we need, well, obviously two pieces of information. The mean difference, which was already calculated, we calculated that as 4. And then we need the estimated standard error of the mean difference, which the formula is right here. Let's go ahead and calculate that, and then we can interpret it afterwards. So S sub m sub d, which is the estimated standard error of the mean difference, is standard deviation 2.12 divided by the square root of sample size, which is 5. So let me go ahead and do that now. And I'm getting 0.95. And the interpretation of this is essentially it's always the same. It's if the null hypothesis is true, this is how much error you should expect. But in this context, what we're saying is that if the null hypothesis is true, meaning there's no difference on average between the before and after scores, you would expect a difference on average of 0.95 due to sampling error alone. That's just random chance. And so essentially now we can calculate our test statistic T in order to see if the difference we found, 4, is substantially larger than what you would expect by chance alone. And so T is 4 divided by 0.95. And I'm getting 4.21. The cutoff was only 2.776, so 4.21 is in the critical region, and so our conclusion then is reject H0, which what that really means is that there is a statistically significant change in scores between the two measurements before and after. So this treatment caused a change in scores. Okay, the next thing we can do is measure the effect size. And recall from the information in the textbook as well as in the module, for t-tests, you can use the estimated Cohen's d, which is a measure of how much distance, how many standard deviations the treatment caused scores to change by. Or you can measure r squared, which is an effect size that measures how much variance is explained by the treatment effect. The formula for r squared is always the same, and so that's something we've already done a few times. Even in the videos, we've done those. So let's just use estimated Cohen's d and interpret it as indicated there. So the estimated d value in this study, we take our mean difference of 4 and we divide by the standard deviation. So it's telling us how many standard deviations on average did scores change by. And so what we get is 1.89. And the cutoff for a large value is only 0.8. And so what you can interpret that as a very large effect. So far we have this. We have that reject H0 means there was a statistically significant change in scores between the before and after measurements, and that effect is very large. So the last thing we can do is calculate the confidence interval. And recall that basically what the confidence interval does is it estimates the true population mean difference using this sample of 5 participants. And so it's like, okay, these 5 people were in your study. Using their information, let's estimate what the average difference in scores would be for everybody that these participants came from. So we're focusing on the population now. And let's go ahead and do that. So we'll do a 95% confidence interval. Just like in the past, we've talked about how if you use an alpha of 0.05, what corresponds to that is 95% confidence interval. 5% is your alpha, 95% will be your confidence interval. The reason that you want to have that match is so that the t value in this formula can be the same t value that you've already identified from your table. So let's go ahead and calculate the confidence interval. 95% confidence interval. So we take our mean difference of 4. We add and subtract the following product. So our critical value of t was 2.776. And we're going to multiply that by our estimated standard error of the mean difference, which was 0.95. So let's see what we have here. So I'm getting 4 plus and minus 2.64. And that gives us 1.36 to 6.64. So we can say that according to our probability estimates, we're 95% confident that the population mean difference is somewhere between 1.36 and 6.64 points. Okay, so that's the essentially all the steps involved in a problem like this. What I want to end this problem with, however, is a conclusion statement as it might appear in a published report. And so let's put that right here. The conclusion statement might look something like this, that the data suggest there is a significant mean difference. Let's just call it that. So the first thing you always have is just a statement in plain English saying what you found. So we rejected H0, and so we're basically just saying that it appears there's a statistically significant mean difference, and then we provide the statistics that allowed us to arrive at that conclusion. So we used a t-test with 4 degrees of freedom, and our test statistic equaled 4.21. P is less than 0.05 since we rejected H0 using alpha of 0.05. What else? We had an estimated D value of 1.89, and I'm going to put very large. And then what else? So we did the 95% confidence interval of 1.36, comma 6.64. Okay, so something like that is your conclusion statement, and that's what might be included when a researcher finishes their study and they go to write up the results so that it can potentially be published in a scientific journal. All right, so that's question number 1. And question number 1 is basically, starting from scratch, from the actual raw data, going through to the actual conclusion. Let's look at a second problem where some information is already provided for us. So this hopefully moves a little quicker. Let's go to that one. Okay, so this one says a repeated measures study with a sample of 9 participants produces a mean difference of 10 with a standard deviation of 6. So already we're given information that we didn't have on the last problem, which is nice. We don't have to calculate the mean difference and the standard deviation of the difference scores like we did in that last problem. So we'll be starting, ahead, if you will. This one, on the other hand, what's different here is it says use a one-tailed hypothesis test with alpha of 0.05 to determine whether this sample showed a statistically significant increase in scores between the first and second measurements. So I just want to focus on that aspect right here, that for a one-tailed test, you're actually checking for a specific prediction about the direction of the change in scores. So you measure people twice in a repeated measure study. There's a before and after measurement, and we want to know if scores went up and whether or not that increase was statistically significant. Because obviously I can already see the average difference was 10. So on average, for these 9 participants, scores went up by 10 points. But is that just sampling error, or is that a statistically significant effect? That's what we're aiming to check when it comes to this hypothesis test. And so, speaking of hypothesis testing, let's start with our hypotheses. And this is a one-tailed test, and so our hypotheses need to reflect that. So we have the null hypothesis and the alternative hypothesis. The alternative is always the one that includes your prediction, the one you care about. And the null hypothesis is always the boring one that basically says, no, nothing's going to change, or in this case, things will not increase. So I'm going to start with the alternative. The alternative is the one that says, on average, scores are going to increase. In other words, the average change is going to be greater than 0. Because if the average change is 0, that means scores did not change. And on the other hand, if scores went below 0, that means scores did not increase. So this is the only way to say that average scores increased. Therefore, the null hypothesis says the average difference score will decrease or equal 0. So essentially, these are our hypotheses. We're doing a one-tailed test, alpha of 0.05. Let's go ahead and find our critical value of t, so that we know what the decision-making criteria is. First, let's find our degrees of freedom. Since there are 9 participants in the study, 9 minus 1 gives us 8 degrees of freedom, and therefore we have all the information we need to go to our t-table. We're using an alpha of 0.05 in one tail, and so that means we're using this heading up here. 0.05, 8 degrees of freedom, gives us a t-value of 1.86. Now, is that a positive 1.86 or a negative 1.86? That's a positive 1.86 because we are looking at potentially scores increasing, which are positive values. A decrease hypothesis would have given us a negative critical value. So it's positive 1.86. I'm going to write that here. T, I'll put critical, just so we know that this is the one that came from the table. 1.886. Was that correct? Let me just double check that. No, 1.86. So always good to double check. You never know. 1.86. So essentially, once we calculate our test statistic of t, if that test statistic is larger than 1.86, we're going to reject H0. Put differently, if it's larger than 1.86, we think that the average difference we're seeing here is statistically significant. It's a statistically significant increase. All right, so let's go ahead and find out what we have. Just like in the last problem, in order to calculate t, you need your average difference for the sample, which is already given to us as 10, and then you need your estimated standard error, which formula is down here. And so let's go ahead and calculate that. All right, so standard deviation of 6 divided by the square root of your sample size. So 6 over 3 is 2. So the interpretation of this value, I really think it's important to know how to interpret these values so you're not just going through the motions. Again, what this value tells us is when the null hypothesis is true, that scores did not increase, you would still expect to see 2 points of an increase due to sampling error alone, random chance. This is just the idea that people are people. And so scores are going to look weird because of random error. But we want to know if the average difference of 10 is significantly greater than what would be expected by chance alone. So let's go ahead and calculate our test statistic of T. Take your sample mean difference of 10, divide by your estimated standard error, and we get 5. 5 is larger than your critical value of 1.86. And so again, in this problem, reject H0, which essentially is saying we believe, according to this data, that there is a statistically significant increase in scores on average as a result of this, whatever treatment is being analyzed in this study. All right, in the last problem, we calculated the estimated Cohen's d. Let's do r squared in this one. Remember, they're both effect size, but they measure different types of, they measure effect size differently. And so let's do r squared this time. R squared is your calculated value of t squared over t squared plus degrees of freedom. All right, and so let me calculate this, and then we can interpret the size. So I'm getting 0.76 after I round to the second decimal, and 0.25 is large. So in this one, we have another very large increase or effect. And while we're at it, let's just calculate a 95% confidence interval. So the average sample difference, mean difference was 10, plus and minus your critical value of t times your estimated standard error. All right, and so it looks like we get 6.28 to 13.72. Okay, and then of course you could write a conclusion statement, but it's going to look very similar to the one we did in the last problem. So let's pause here, and that essentially is 2 questions looking at repeated measure studies or within subjects designs, basically from start to finish. And so step by step through these problems. As always, I encourage you to look in the textbook for additional examples. The authors go step by step through other problems. The study guide is posted onto our course website, and let me know if you have questions.